Welcome to Calculus. Today we will investigate approximating area with Riemann sums and trapezoidal sums. We'll take a look at one example. We've got a function here, f of x equals x cubed plus 5, and we're considering it over the interval from 0 to 2. So I've got a graph of the function here, and what we are after is we want to approximate the area under that curve using four different types of sums. So we want to start by using a right Riemann sum, then compare it to what a left Riemann sum would give, then a midpoint, and then finally a trapezoidal sum. So what we'll do is we'll start off by considering the right Riemann sum. So remember, we want to start off by deciding what our delta x, or really the width of these rectangles, is going to be. And so we just really need to take the interval, if we call this a and b, according to the formula b minus a over n. And n is the number of subintervals. So we see here we got 4 subintervals. So for us, this is going to be 2 minus 0 divided by 4. So that's going to be 2 over 4 reduced down to half. And that makes sense according to the graph. Each of these 4 rectangles needs to be a width of half. So we'll start drawing them with our right endpoint on the function. And again, the graph helps us to visualize really what kind of approximation we're making, and also along the way decide if it's an overestimate, an underestimate, or really close to the actual value. So there's a visualization of the right endpoint partitioning of the area under that curve. So let's calculate the area of this right Riemann sum. So what we need to remember from geometry is the area of a rectangle simply is length times width. So we'll start off, and really what we need is to find what are the function values at these right endpoints. So I want to create a table, and we'll put our intervals. So we're starting at an x value of half, since that would indicate the right endpoint. And then we'll climb up by halves, so 0.5, 1, 1.5, and 2. And then we just want to calculate what the function value is going to be at those numbers. So at 0.5, we're going to cube that and add 5. So that's going to be 5.125 if I cube that. 0.5 times 0.5 times 0.5 is 0.125. At 1, we're going to cube it and add 5. That'll give us 6. So that'll be for that second rectangle. Its right endpoint's right there at 6. At 1.5 cubed, let's see what the value of 1.5 cubed is. So if you don't remember, you can multiply 1.5 times 1.5 times 1.5. So that's 3.375. If I add that to 5, that's 8.375. And 2 is going to have the value of 2 cubed plus 5. And that's 8 plus 5, which is going to have the value of 13. So essentially what those represent are the heights of the rectangles. I know each one is half wide. So for my right Riemann sum here, we'll say that it's going to equal half times, so we can think about it as 4 separate areas added up. So it could be half times 5.125. That's the first rectangle there, plus half times 6 plus half times 8.375 plus half times 13. Another way to represent that would be as half, if I factored it out, times the sum of the heights, 5.125 plus 6 plus 8.375 plus 13. Let's calculate it according to that second way of writing it. So we'll just find the sum first. 5.125 plus 6 plus 8.375. And lastly, plus 13. So the sum of the four heights is going to be 32.5. And then half of 32.5 is going to be 16.25. So our first estimation, the right Riemann sum is going to be 16.25. Well, let's compare that to a left Riemann sum. So what we'll do is let's take our graph here and copy it, and we'll just calculate the left one right below it. So for a left Riemann sum, we still have to have 4 subintervals, but instead of my right endpoint being on the function, I'm going to have my left endpoint be in the function. So again, to visualize, I'll just create these rectangles. So notice if we start to think which one's going to be an overestimate, which one's going to be an underestimate, definitely we can see with this version, because the left endpoints are on the function, it's going to be an underestimate. I've got these gaps here between the rectangles in the graph. So an initial feeling for at least in this case with this function, the left Riemann sum should be smaller than what we calculated for the right Riemann sum. Well, again, what's going to help us here, we know the width, our delta x, is going to be 1/4. That hasn't changed, or I'm sorry, 1/2. That hasn't changed. But let's investigate about our heights of these rectangles. Notice, because again, we're on the left side, the heights are different. So we'll calculate again x and f of x along the same subintervals. So here we're going to actually start with 0. So about to write 0.5, but again, that's the first left endpoint is at x value of 0, 0.5, 1, and at 1.5. So notice even our domain's different. It shifted half to the left. Now we've already calculated some of these. So just to remember, we calculated the value at 0.5 to be 5.15. Sorry, 5.125. 1 was at a value of 6, and 1.5 at a value of 8.375. All we've got to calculate is at 0, and since the function is x cubed plus 5, it's 0 cubed plus 5, which is 0 plus 5, or 5. So for this sum, the way we're going to set it up, very similar to the way we set up the last one. Now that we've got these heights, the left Riemann sum is going to be 1/2 times 5 plus 1/2 times 5.125 plus 1/2 times 6 and plus 1/2 times 8.375. Again, a good way to calculate that's to factor the width, or the delta x, to the far left, and then add these heights up. 5 plus 5.125 plus 6 plus 8.375. So again, we just need to calculate that. Let's find that sum first. So adding up those heights, those are 24.5. And then half of 24.5 is going to be 12 1/4, 12.25. So again, if we compare that to what we saw from our right Riemann sum, definitely we see a big difference. So definitely for this one, the right endpoint's an overestimate, the left endpoint's a underestimate. And that gives us a good transition to the midpoint Riemann sum. So again, let's pick it up. We'll get rid of these. And consider now if I were to have subintervals whose midpoints were on the function. So again, to draw, it's helpful because I'm going to visualize it. So if I had the midpoint of my rectangle right on the function, that's how I want to place my rectangles now. So I'm just placing the midpoint of each rectangle. So notice this is really splitting the difference. And as we can see, it really is attempting to account for the overestimate of the right one, the underestimate of the left endpoint, and hopefully come up with a better approximation. So this, again, let's just announce as the midpoint Riemann sum. So again, helpful here, I know my delta x is going to be half. That has not changed. But we need to find our modified table. So we'll do x, f of x. And so if we're thinking about midpoints, I'm not going to start at 0. I'm not going to start at half. I'm going to start between them. So 1/4. And then I'm going to add half to each. So 0.75, 1 1/4, and 1.75. So it's a different domain. And for these, let's calculate the values. So I just want to place these in our function. So I know I got to cube the x value and add 5. So we'll start off with 0.25 cubed and then add 5. That's going to be 5.0156. We'll do the same with 0.75, so let's cube it. So that's 0.4219, 5.4219. And then let's cube 1 1/4. 1.25 cubed has the value of 1.9531. Add 5 to that, which would give us 6.9531. And lastly, we'll cube 1.75. That's 5.3594. That's going to be a value of 10.3594. Again, let's calculate the area of those 4 rectangles by multiplying the delta x times each of these heights. So we'll have half times 5.0156 plus half times 5.4219 plus half times 6.9531 plus half times 10.3594. And again, a good arrangement to calculate the actual values, factor out the half, add up these 4 heights. All right, so we got the sum written. Let's calculate it out. So again, let's start with just adding that up. 5.0156 plus 5.4219 plus 6.9531 plus 10.3594. That's 27.75. I take half of 27 3/4. That's going to give us 13.875. 13.875. So again, that's an approximated area. So I do want to compare it to what we saw with our left and our right. We should see that it's somewhere in between. So definitely it's bigger estimate than our left endpoint. That was at 12.25. And a smaller estimate than our right endpoint. That was 16.25. So definitely if we think about like what's more accurate, which is less prone to error, over or underestimate, probably the midpoint Riemann sum is a good one. Let's compare that again with our final sum. So it's not a Riemann sum, it's called the trapezoidal sum. And instead of using rectangles, the trapezoidal sum uses trapezoids. The trapezoidal sum. Again, let's visualize it. So the way that these are trapezoids really has to do with the nature of the upper side of this quadrilateral. So the three lower ones don't change. But instead of just putting my rectangle at the left endpoint or the right endpoint, what we'll do is we'll create a secant segment, like a chord, that connects the left with the right, and we've got a trapezoid. And so you can see that the quadrilaterals that we're forming are much closer to the actual curve than even our midpoint rectangles. And we'll finalize here with that fourth trapezoid. So again, the graph helps us to visualize it. So for this one, what we'll need, we need to find the length of all the sides from 0 going up by halves all the way to 2. So when we create a table here, and it'll bear out when we try to calculate the area of each trapezoid. So we'll put 0, and then we'll count up by halves. Half, 1, 1.5, and 2. I need all 5 here. F of x. So we'd calculated these before. 0 had the value of 5. Half, if you recall, has the value of 5.125. 1 has the value of 6. 1.5 has the value of, we check our last one, 8.375. And 2, again, I probably can just calculate that. It's 2 cubed plus 5. That's going to be 13. Now, the reason why I need all 5 instead of just 4 of them is because now I'm considering area of trapezoids. So our delta x, or the width, is still going to be half. So we just need to remember geometrically how we calculate area of a trapezoid. So let's just draw a trapezoid to stand for all trapezoids here. So remember, the way we calculate the area, it's really an average of the heights. We call these base 1 and base 2. They're parallel to each other. And the area is going to be half their sum. So it's the average of the two bases times what we'll call the width, delta x. Now we're going to do that for each one of these trapezoids. So we got to create 4 of those. So let's start off. We'll just set it up here. It's going to be half. So I'm going to consider the 2 heights of the first trapezoid. So it's going to be 5 plus 5.125. And I'm going to multiply that times delta x, which is half. Again, we'll do that for the second one, plus half. Now the second trapezoid, its left side's 5.125, its right side is 6. We'll scroll around here so we don't run out of room. So, oh, okay, and I do need to multiply by delta x half. Half times, now I'm going to have left side of 6. This is the third trapezoid. Right side of 8.375. And lastly, half and 8.375. That's the left side of the fourth trapezoid plus 13. And again, I'm forgetting my delta x's, so don't want to forget that. So I see for each one of these, I got a half in the formula for a trapezoid area and a half as my delta x. So I'm going to factor out basically a quarter. And I'm going to factor that out of each one. And it's going to be times this sum, so the repeated sum, 5 plus 5.125 plus 5.125 plus 6 plus 6 plus 8.375 plus 8.375 plus 13. So you can get a sense of how it's really an average. When we're treating these as trapezoids, it introduces the idea of the average of the heights of each quadrilateral. Let's calculate this. So again, we want to find that sum first. So I just want to add it up. 5 plus 5.125 plus 5.125 plus 6 plus 6 plus 8.375 plus 8.375 plus 13. So notice in the sum, the only values, the heights we don't repeat, are the first and the last, the far left and the far right. And let me make sure I got pluses instead of equals. That adds up to 57. So then what we want to do is multiply that by a quarter. So 0.25 times 57 gives us 14 and a quarter. So again, we want to compare with the others, really with the midpoint, because we saw that the midpoint Riemann sum was in between the left and the right approximations. So when I compare this, it's as a trapezoidal sum, it's between the midpoint and the right Riemann sum. So again, it probably would be useful just to consider how they're organized. My extreme underestimate is going to be the left Riemann sum at 12.25. The next one is going to be the midpoint Riemann sum, 13.875. Then the trapezoidal sum, 14.25. And the extreme overestimate would have been 16 1/4. Well, thank you for joining for this investigation of approximating area under this cubic function using 4 different ways of approximating with quadrilaterals, 3 with rectangles, a left endpoint, a right endpoint, a midpoint, and then the trapezoidal sum. We'll keep our eyes about us for which one is going to be the best approximation, and that'll be easier once we are able to take integrals and find the exact integral and make a direct comparison. Again, thanks for joining. See you soon.